In this video, I'm going to explain how to solve the questions in this February-March 2024 paper 2. Question 1a, we are asked to draw a label diagram to show the metallic bonding in bismuth. Bismuth is an element in group 15 of the periodic table, and the question tells us that it has metallic bonding. Right, metallic bonding is electrostatic forces between cations and delocalized electrons. So we need to draw cations. So let's draw circles to represent cations. Right, I'll draw 3 rows of them because that is what is shown in the past year mark scheme. Now, I'm going to label them as cation. Then I'll draw negative charges between them to represent the sea of delocalized electrons. And I'm going to label them as delocalized electrons. In part B, the question tells us a reaction between bismuth and water. Bismuth oxide is formed, and also a gas, they will make a squeaky pop sound, with burning splint. Tell us that hydrogen gas is produced. So let's write down the reactants, which is bismuth and water, H2O, forming bismuth oxide, Bi2O3, and hydrogen gas. Now we can do the balancing. So I need 2 bismuth. And let's balance the number of oxygen first. I have 3 oxygen here in bismuth oxide. So that means I will need 3 water molecules because each water molecule contains only 1 oxygen. So I need 3 of them. After that, we can balance the number of hydrogen. 3H2 here, so 3H2 on the right hand side also. Now B2, we are told that bismuth oxide is yellow insoluble solid that melts at a very high temperature. This compound, when it is melted, it conducts electricity. So we are supposed to deduce the structure and bonding. So you are supposed to give these 2 in the answer to score the 2 marks. So let's talk about the structure first. It has a very high melting point. So that tells us that bismuth oxide has a giant structure, right? It is giant ionic because it will conduct electricity in its molten form. So giant ionic structure. Now we have to explain the answer. Do not just write the structure, because now if you do not know how to find the charge, you can always write between cations and anions. So second point will be ionic bonding. Explain because they are free moving or mobile charged particles in the molten compound. In part C, we are given an equation showing that bismuth oxide can react with sodium oxide to form a compound, sodium bismuth. So in part 1, we are supposed to deduce the oxidation number of bismuth in bismuth oxide and also in the product. In bismuth oxide, 2 bismuth, so I'm going to put as 2x unknown plus 3 oxygen. Now oxygen oxide always have a negative 2 oxidation number. Overall, it has a 0 charge. No positive or negative, so overall it's a 0 charge compound. So we can find X from here. X is positive 3. Right. In the product, sodium bismuth, we have sodium, a group 1 metal, which will always have a positive 1 oxidation number. Again, bismuth unknown, plus X. 3 oxygen, negative 2 again. Overall, no charge, so 0. Find X, we'll be able to deduce the oxidation number of bismuth in this compound, which is positive 5. Part 2, we are supposed to identify the reducing agent in equation 1. So we have found the oxidation number of bismuth as plus 3 here in bismuth oxide and in the product plus 5. Let's find the oxidation number of other atoms also in the equation. Sodium is still plus 1 here, oxygen negative 2. Oxidation of any atom in an element, okay, will be 0. So here oxygen is negative 2, sodium is still plus 1. So let's see what has changed. Okay. Sodium oxidation number doesn't change, okay, from the beginning until the end of the reaction. Oxygen negative 2 to negative 2. But here we have another oxygen, right? Sorry, I missed out this one, negative 2. Now we have another oxygen here, 0 to negative 2. Okay, there's a reduce in the oxidation number of oxygen from 0 to negative 2. So oxygen here undergoes reduction. Right, now for bismuth, from plus 3, positive 3 to positive 5 here. So oxidation. Reducing agent means a species that undergoes oxidation, okay, and also its oxidation number has increased. So the reducing agent is bismuth oxide. Now in part D, we are given a reaction. So X is forming Y and Z in the reaction with sodium bismuth as oxidizing agent. So part 1, we are supposed to explain the term oxidizing agent. So oxidizing agent is a substance that gains electrons and is reduced. In part 2, it's about a reaction that is forming X. Compound X forms when methyl butene reacts with potassium magnate 7. So let's write the structure of methyl butene and see how it forms X. Okay, butene means I have 4 carbon. Double bond is between carbon 2 and 3. And then I have a methyl group here. It's H, right? So this methyl butene is forming X in a reaction with KMnO4. So if you look at X and methyl butene, you realize that what has changed will be no more double bond between the 2 carbon. And now each carbon is bonded to an OH group. Right, it became a diol. So reaction between alkene and KMnO4 and forming a diol, we have to use cold dilute acidified KMnO4. Now, part 3 will be about compounds Y and Z reacting with different reagents. So let's look at compound Y. It has the C double bond O functional group, and the C in the functional group is bonded to 2 alkyl groups. So Y is a ketone. Okay, let's look at the other compound Z. It has a C double bond O functional group as well. Okay. On the right hand side of this carbon, there's an alkyl group, but left hand side there's a H. So Z is also a of carbonyl compound, but it is not ketone, it is an aldehyde. So now let's look at the reagent given to us. The first one would be sodium carbonate. Sodium carbonate is a weak base. Now we have a ketone and an aldehyde here, so both will not react with sodium carbonate because they are not acidic. So no reaction with Y and no reaction with Z. Now let's look at the second reagent, alkaline iodine. Alkaline iodine can test the presence of CH3CO in the structure of carbonyl compounds. So let's look at why. Okay, CH3CO, there's a part of CH3CO here. So Y will give a positive result with alkaline iodine to form yellow precipitate. That yellow precipitate is triiodomethane, CHI3. Now let's look at Z. Does Z contain CH3CO also in its structure? Okay, yes, there's a CH3CO here. So it will also give a positive result with alkaline iodine. Also forms triiodomethane. So the observation is also yellow precipitate. Now let's look at the third reagent, 2,4-DMPH. 2,4-DMPH will give orange precipitate with any carbonyl compound, right? It is a test to identify the presence of carbonyl compound in any unknown solution. So why ketone is a carbonyl compound? See, aldehyde is also a carbonyl compound. Both will give orange precipitate with 2,4-DMPH. The last one, Tollens reagent. Tollens reagent is a mild oxidizing agent which is only able to oxidize aldehyde, okay, but not ketone. So we have Y, a ketone, Z, and aldehyde. Only Z will give positive result with Tollens reagent, and the positive observation will be silver mirror. Because Tollens reagents contains silver ion, which can be reduced to silver, Y as a ketone will not be oxidized by Tollens reagent, so no reaction. Part 4, we will construct an equation for the reaction of Z with a reducing agent NaBH4. So Z is an aldehyde. So let's say I start with CH3, this CH3 here, and CHO for the functional group of aldehyde. So Z will react with reducing agent. We always use square bracket H to represent an atom of hydrogen from reducing agent. So reduction of aldehyde will give us primary alcohol. CH3 has no change, right? The functional group CHO will become a primary alcohol, CH2OH. Now, that's the only product. So let's see how many hydrogen atoms are needed from the reducing agent. From the left Z to the right primary alcohol, I have used 2H, right? From 1H here to 3H. So plus 2 hydrogen atoms from the reducing agent. If you're wondering about whether or not you can use molecular formula to write the equation, the answer is no, because you are given the structure of Z. It means you'll be able to write structural formula of Z instead of using the molecular formula. You're only allowed to use molecular formula if the structure of the compound is not given to you. The final part of question 1, okay, part E, we are given a second equation here showing was the reaction between manganese 2 and bismuth ion in the ratio of 2 to 5. And then there's a description of the procedure of an experiment. 100 centimeter cube of a saturated solution of manganese 2 is added to volumetric flask. Okay, distilled water is added to make the solution into 1000 centimeter cube. 1 decimeter cube is 1000 centimeter cube. Right, so this is actually a dilution from 100 to 1000. So this is a 10 times dilution, right? The concentration of the solution will become 10 times lower compared to the saturated solution. After that, 25 centimeter cube of that diluted sample is titrated with a sodium bismuth solution, 0.100 mole per decimeter cube of concentration. And using this information given, we are supposed to calculate the concentration of manganese in the original solution before dilution. Okay, the title of the sodium bismuth solution is 21.5. So I'm supposed to find the number of mole of bismuth ion because I have the volume and also the concentration. I can use the formula MV 1000. This will give me 2.15 times 10 to the power of negative 3 mole. Right, having this number of mole of bismuth and the mole ratio in the equation, I'll be able to find the number of mole of manganese 2 ion, which is 2.15 times 10 to the power of negative 3, okay, times 2 over 5 because of the mole ratio here. 8.60 times 10 to the power of negative 4 mole. Then I can find the concentration of manganese 2 in diluted solution. Concentration will be number of mole divided by volume. So we use 25 for the titration. And I have the number of moles of manganese 2 in the 25 centimeter of the solution. So number of mole divided by the volume. Change the volume to decimeter cube. So that will be 0.025. The concentration of manganese 2 in diluted solution will be 0.0344 mole per decimeter cube. Now, when we did dilution, we diluted the saturated solution 10 times. So that means the concentration of manganese 2 in saturated solution will be 10 times higher than this. So I use this concentration of diluted solution and multiply by 10. This will be the concentration of manganese 2 in saturated solution. We have come to question 2, a question about chlorine. So in this table 2.1, we have information about chlorides of period 3 elements. So chloride of sodium, the formula will be NaCl. So there's a group 1 metal, so you always form a +1 charge cation. Chlorine in group 17 will need 1 electron from sodium to achieve octet, so they form a +1 and -1 ionic compound. So NaCl is the formula. Magnesium in group 2, so we need 2 chloride ions. And silicon group 14. Now, sodium chloride is a giant ionic structure. Same goes to magnesium chloride. Okay, metal and non-metal. Now, moving towards p-block elements in a period, okay, they start forming covalent compound here given to us. So it is a simple covalent compound. is ionic. Now, ionic compounds dissolve in solution, no reaction. So pH is 7. Simple covalent compound hydrolyzes in water to give acidic solution. So the pH is acidic. In part B, when chlorine reacts with cold sodium hydroxide, chlorine is both oxidized and reduced. Right? And this type of redox reaction is called disproportionation. Disproportionation of chlorine with cold sodium hydroxide will produce sodium chloride and sodium chlorate, NaClO. In part 3, we are supposed to write an equation for reaction between chlorine and hot sodium hydroxide. So that means the change in oxidation number of chlorine will be larger compared to with cold sodium hydroxide. Chlorine will react with sodium hydroxide, hot sodium hydroxide, to form sodium chloride and sodium chlorate, this time NaClO3. Okay, with cold sodium hydroxide, the change in oxidation number is not so great, so it only forms sodium chlorate, we only one oxygen. With hot sodium hydroxide will be 3 oxygen in the compound, and water is also formed. Now let's balance the equation. Right, I will need 3Cl2 here, 6 sodium hydroxide, 5, and 3 water. Part 4 of this question, we are supposed to describe fully what is observed when silver nitrate is added to aqueous solution of the chloride of sodium, followed by dilute ammonia solution. So sodium chloride solution contains chloride ions. Silver ion from silver nitrate solution will react with chloride ions to form an insoluble solid, which is silver chloride, a white solid. So white precipitate will form. Right after that, okay, followed by dilute ammonia. So what will happen? Silver chloride solid will dissolve. So white precipitate, okay, it will disappear because it dissolves in dilute ammonia solution. Part C, chlorine will also react with phosphorus to form phosphorus chloride, PCl5. It is a simple molecule. It also exists in another two forms, PCl4 ion, positive ion, and PCl6 ion. Right, it starts from PCl4 here given to us the shape is tetrahedral. So we are supposed to identify the shape for PCl5 and PCl6. Now PCl4 is tetrahedral. That means PCl4, the P has no lone pair and is bonded to 4Cl. So we have equal repulsion between the 4 bonding pairs. The shape is tetrahedral. So moving to the left, okay, we have extra 1Cl bonded to the P in the middle. So no lone pair. Okay, but bonded to 5 chlorine. So again, equal repulsion between the 5 bonding pairs. So this should give us a trigonal bipyramidal shape. Right hand side, we have phosphorus now bonded to 6 chlorine. Okay, overall charge negative here. So 6 bonding pairs, no lone pair, equal repulsion between 6 bonding pairs. We get octahedral. PCl5 will react with J to form H3PO4. So PCl5 to H3PO4, right? You can see that from P here, you have additional H and O. So J is H2O, water. Now, any compound reacting with water, the type of reaction is called hydrolysis. Part D, reactions of chlorine again. This time, chlorine reacts with propene to form K12-dichloropropane. Right? K then can be used to form L. So we are given a reaction scheme here. We are going to use it for the later parts of D. Now, part 1, we will complete this mechanism for reaction between chlorine and propene, which is an addition reaction, electrophilic addition. Now, in this mechanism, we have to include charges, dipoles, lone pair of electrons, and curly arrows as appropriate. So let's draw the dipole, partial positive, partial negative. Now, once this chlorine molecule, which was actually non-polar, once it approaches the double bond between these two carbon, the electrons here and these 4 electrons in the double bond will repel one another. So induce a dipole in this chlorine molecule. So it became partial positive here, the one that's closer to the double bond. Then the pair of pi electrons, we need to show an arrow from the pi electrons to the partial positive chlorine. After that, the breaking of this Cl-Cl bond. In the middle, we have an intermediate. This pi bond is broken. No change to the 4 groups bonded to the 2 carbon. One new bond is formed between C and Cl. Now, this chlorine took both the electrons from the Cl-Cl bond, became a chloride ion. Here, the carbon is electron deficient, so it has a positive charge. And then, show a curly arrow from the lone pair to the positive carbon in the carbocation ion. At the end, we get the product. Part 2 is about reaction 2. We need to identify the reagent and conditions for reaction 2. So from K to L. We have chlorine here, CH3, no change. What is eliminated from K to L will be HCl. The H that was here, and this Cl. So remove this H, remove this Cl, we get L from K plus HCl. This is an elimination reaction from halogenal alkane to an alkene. So the reagent and conditions used in reaction 2 will be sodium hydroxide in ethanol. Condition will be heating. In part 3, we will draw one repeat unit of the addition polymer that forms from L. Okay, this is an alkene. So let's draw a repeat unit. The 2 carbon, there's a CH3 here. The other carbon is bonded to 2 hydrogen. So this is one repeat unit. So one repeat unit involves only one monomer molecule. Remove the pi bond. Add 2 dangling bonds on the left and right of these 2 carbon to show that it is a polymer. These 2 dangling bonds for polymer must be longer than the usual covalent bonds that you're drawing for the other parts of the molecules to show that this is a polymer. Question 3 focuses on nitrogen. A, we are supposed to give two reasons to explain the lack of reactivity in nitrogen. The first one will be a strong triple bond between the two nitrogen atoms. Second reason will be molecule is non-polar. Non-polar molecules are not attacked by nucleophiles or electrophiles. That explains the lack of reactivity of nitrogen molecules. Part B, we are given three equations. So part 1, we are supposed to write an equation to show the formation of a mixture of NO and NO2 in reaction 1. Right, we have nitrogen reacting with oxygen, forming nitrogen oxide and nitrogen dioxide. So let's balance the equation now. We have 2N here. Okay, number of nitrogen atoms is balanced. So I have 3 oxygen on the right hand side. That means I need 3/2 O2 on the left. Part 2, we are asked to give the formulae of the products of reaction 2. It says products, that means there are more than one product. NO2 is reacting with water. That means it will form HNO3 and HNO2. Let me write down the first combination of answer, HNO3 and HNO2. Now, there's another answer that can be accepted. If you put 3 nitrogen dioxide to react with H2O, you will be able to get 2 nitric acid and nitrogen monoxide. So the other set of answers will be nitric acid and nitrogen monoxide. Nitrogen dioxide is an acidic oxide, so it reacts with water to form nitric acid. Now, if nitric acid is formed, it is an oxidation reaction from nitrogen dioxide from +4 to +5. So that means there is a reduction reaction also. Is how I deduce that nitrous acid is also formed. I can do the same for the other set of the answer. There's another redox reaction. Now the part 3 of this question is asking for one environmental consequence of reaction 3. Now reaction 3, there is a PAN compound that is formed between nitrogen dioxide and unburned hydrocarbon. Right? Now this PAN will only cause one environmental consequence, which is photochemical smoke. Part C is about Haber process because it involves nitrogen as one of the reactants. We are given the equilibrium for Haber process with the delta H. Now we will use this information to complete table 3.1. We are supposed to give the enthalpy change of formation for the reactants and also the product. Now the two reactants are elements, nitrogen and hydrogen. Enthalpy change of formation means one mole of the compound is formed from its element. So if I am to write an equation to show the formation of nitrogen, there will be 1 mole of nitrogen forming 1 mole of nitrogen gas. There's no change from the reactant's product. So there's no change in enthalpy also. So the enthalpy change of formation for all elements are 0. For ammonia, let's write an equation to show the formation of ammonia. To form 1 mole of NH3, I will need half a mole of N2, 3/2 moles of hydrogen gas to form 1 mole of ammonia. Can you see that this is exactly the equation given to us divided by 2? Okay. Let's have this equation, then we'll be able to get the equation for the formation of 1 mole of ammonia gas. That means the delta H for formation of ammonia will be enthalpy change of Haber process divided by 2. That would give us negative 46. Part 2 will explain how the presence of a catalyst affects the reaction. So adding catalyst will increase the rate of reaction. Okay, how? By providing an alternative pathway, and that alternative pathway has lower activation energy. The next part is how would the rate of Haber process change if the pressure is lowered? So that we will refer to the equation. On the left hand side, the reactants are in gaseous form. So changing the pressure will change the concentration of the reacting particles. Lowering the pressure will reduce the concentration of the reacting molecules. So that means the rate of the process will decrease. Because concentration of reacting gas molecules decreases, less gas molecules in a given volume. So frequency of successful collision or effective collisions will also decrease. Part D is about another compound of nitrogen, N2F2. Question tells us that N2F2 molecule has a double bond between its nitrogen atoms. So here we are supposed to show the dot and cross diagram for N2F2 molecule. Now let's draw the double bond. We have the 2 nitrogen atoms here. Although they are of the same element, adjacent atoms we always use different symbols for their electrons to show different electrons from different atoms. So I'm going to use cross for nitrogen on the left, double bond, so 2 electrons from nitrogen on the left and 2 electrons from nitrogen on the right. So I use dots for nitrogen on the right. Nitrogen is from group 15. It has 5 valence electrons. So I've used 2 here. That means 3 more. 1 more sharing with fluorine. So I use the same symbol, cross and cross here. So that means for this fluorine on the left, I can use a dot. Now same goes to this right hand side. Okay, 1 more dot from this nitrogen and fluorine on the right hand side, I'll use cross for its electrons. Nitrogen, again 5 valence electrons, I've used 3 here, so 2 more will be lone pair. This one, lone pair. Fluorine on the left, fluorine is from group 17, it has 7 valence electrons. Okay, we have used 1 here, so that means 6 more, 3 more lone pairs. Okay, Do the same for fluorine on the right hand side, 3 more lone pairs, but this time we use cross, okay, because we have used cross here. So this would be the dot and cross diagram for N2F2 molecule. In part 2, we will deduce the hybridization of the nitrogen atoms in N2F2 for carbon, nitrogen, and oxygen. If they are surrounded by all single bond, no double bond, all single bonds, hybridization will be sp3. If there is one double bond, hybridization will be sp2. If one triple bond, okay, sp hybridization. So if you look at this compound, N2F2, nitrogen has a double bond here between the two nitrogen atoms. So every nitrogen has a double bond. So the hybridization is sp2. Now, part 3, we have to draw a diagram of the pi bond between the nitrogen atoms. Okay. In the previous part, we have learned that nitrogen has a double bond between the two nitrogen atoms. So now we are supposed to draw this pi bond and then describe how it is formed. So pi bond will be the sideways overlapping of two p orbitals. So we can draw like this, show two p orbitals, each from the nitrogen atoms, and they overlap sideways. Okay? Or you can also draw the pi bond as two electron clouds above and below a sigma bond. Okay, so answer can be this on the left or the one on the right hand side. Now the description will be sideways overlapping of adjacent p orbitals, right? They are adjacent next to each other above and below the sigma bond. We have come to the last question of this paper, question 4. We have a reaction scheme here from P to S. It tells us that P, Q, R, and S, all four of them show stereoisomerism. So there are two types of stereoisomerism, geometrical isomerism and optical isomerism. So we are supposed to deduce which type of stereoisomerism is shown by P, R, and S. The one for Q is given because the structure of Q is not given to us here. So P has a double bond, and each carbon in the double bond is bonded to two different groups of atoms, right? One hydrogen, one alkyl group, so two different groups of atoms. The other carbon also two different groups of atoms. So it shows geometrical isomerism, or what we usually call cis-trans isomerism. Now, R and S, we don't see double bond anymore. So that means they cannot show geometrical isomerism. The easiest answer would be optical isomerism. But the explanation will be they have a chiral center. This carbon here is bonded to four different groups of atoms: hydrogen, nitrile, CH3, then here ethyl group, CH2, CH3. Right? This is a chiral carbon. In S compound S, there's a chiral center also. This C bonded to a hydrogen, bonded to a methyl group, an ethyl group, and COOH. They are all different. So a carbon atom that has four different groups attached is a chiral center. This molecule is chiral. They have optical isomers. B, we will give the structural formula of Q. So starting from P and alkene, reacting with HBr. So this is electrophilic addition reaction. Q will be alkene. Initially, carbon on the left is bonded to one H and one Lq group. Right hand side also one H and one Lq group. Addition reaction, so one product is formed from two reactants. So that means the H and Br will be added to molecule P. So this is the structure of Q. So let's write the structural formula for Q since we already have the structure here. Start from the left hand side, CH3, CH2, CHBr, CH3. Now reaction 2, now that we know Q is actually a halogenal alkane, and from Q to R, Br bromine atom here is replaced by a nitrile group. So this is a substitution reaction. The C here in Q is partial positive because bromine is more electronegative. So KCN here in ethanol, the cyanide ion is acting as a nucleophile and it attacks the partial positive carbon. So this reaction, the full name will be nucleophilic substitution. Right, part 3 is to complete the equation for reaction 3. So reaction 3 from R to S, from nitrile to COOH, this is a hydrolysis of nitrile. So here we are given the molecular formula of R, so that means we can use molecular formula from the beginning until the end. H plus here, the reagent. Now this is hydrolysis, that means water will be involved in this equation. So let's write water. S is formed. S has 1, 2, 3, 4, okay, 5 carbon. So that means from C4H9 here, no change. Then Cn becomes COOH. Okay, so now let's look at what is the other product. So we have C4H9, COOH. So this OOH is actually from the water. Now I need two O, so I need two water molecules. So if I use two water molecules here, I still have H plus. So that means the N will form ammonium ion. Right? N reacts with H plus ion becomes NH4. Part C will be reaction between S and T to form U. There's some data given to us here for U. It is from its mass spectrum. We have the relative abundance of the M plus peak and M plus 1 peak. We can use this information to calculate the number of carbon atoms in U. Right, the question in part 1 tells us that U contains 7 carbon. So let us prove that by using the data. The formula to calculate number of carbon atoms in a molecule by using data from mass spectrum will be, so we'll be able to get that this is 6.94. If we round it up, it would be 7. In part 2, we are given the infrared spectrum of U. For easier comparison, so I put the table of the absorptions here. three main peaks. This one on the left, around 3,000, slightly less than 3,000, 2,900. So it belongs to the CH bond. Now this absorption is not so useful to us because it doesn't tell us anything about the functional group, because most compounds contains CH bond. So let's move on to the next absorption. On the right hand side, this is around 1720. So it belongs to carbonyl, carboxyl, or ester bond, C double bond O in any of these functional group. So we cannot rule out any of them by only finding one bond, one absorption. So let us move to the other one, the other main absorption on the right hand side, which is around 1200. Okay, it belongs to C single bond O bond. Okay, a compound with C double bond O, C single bond O. So that tells us that U is an ester because of the C double bond O bond and C single bond O. So let's check with this equation. S is a carboxylic acid. It reacts with T to form U. One water molecule is eliminated. This is a condensation reaction. Carboxylic acid will only undergo one type of condensation reaction, which is formation of ester. So that also will give us a clue that U is an ester before looking at the infrared spectrum. Now that we know U is an ester, we'll be able to answer this part of the question. So the functional group of ester is also called ester. Now you can refer to the syllabus content. There is a table for the name of all functional groups for all homologous series. So for ester, it is still called an ester. So the name here is written this way. The explanation will be, we have to give the two absorptions for C double bond O and also C single bond O. The first one will be absorption at this range 1710 to 1750 wave number. So we just follow the range is given in the table. This table will be given in the question paper, so you do not have to remember them. And what does it mean by this absorption? It shows the presence of C double bond O. And the next absorption is for C single bond O at the range here given in the table. So let's just write down and copy the range from the table given this wave number, and it shows the presence of C single bond O bond. Last question of the paper. S is forming U and ester, and U is an ester with 7 carbon. So T is an alcohol. Because carboxylic acid will react with alcohol to form ester. Now S is a carboxylic acid with 1, 2, 3, 4, 5 carbon. U an ester with 7 carbon, that means 2 carbon from the alcohol. T is an alcohol with 2 carbon. So T is ethanol. So U, an ester formed from a 5-carbon carboxylic acid and ethanol, its structure should be. And let's also put the structure of T in this box and ethanol. Now, when the question says draw structures of T and U in the boxes, question does not specify which type of formula that you should use. That means you can use any type of formula, and I'm using skeletal formula here.